We are ready.
Yes. Start.
A very good morning to all. Respected distinguished guests, faculty members, research scholars, and all my dear friends. I welcome you all to the second day of National Seminar on Fractional Calculus and Dynamical System. I am Anasri Sompo. I wholeheartedly welcome you all. So let us dive into the insightful talks lined up for today's event. We will start with the interesting topics like fractional operators, mod fractals, chaotic dynamics of fractional value system for El Nino, maps and complex fractional order, stability, and dynamics. Those talk promise to highly informative and engaging. And we are honored to have Dr. Nikam serve as our chairman person. Now, I would like to request Dr. Nikam sir, Dr. Kedar sir to give something to Dr. Nikam sir.
That is. fractional पाहिजे आपण दोन पीट इंटू स्पीकर्स टाईम नाही का हे बघ. दहा 25
I request Dr. V.R. Nikam sir to come on stage to introduce Dr. Anil Gangal sir.
नाही ठीक आहे त्याच्यात येतो आपण.
Good morning, everybody.
नको ते नको काढून घे. ते आवाज चांगला नाही हा चांगला.
Good morning. And I'm very much thankful to Kedar sir and his team for giving me an opportunity of chairing the session. Again, I would like to welcome to Professor Dr. Anil Gangal sir for the invited talk on fractional operators on fractals, construction and potential uses. First of all, I would like to introduce Gangal sir. He is PhD in theoretical high energy physics in 1981 from the Tata Institute of Fundamental Research. After that, he worked as a Wissenschaftler Mitarbeiter research assistant in the University of Karlsruhe in Germany up to the 1983. He worked in the physics department of Pune University till 2010. After that, he worked in ISER up to December 2016 as a visiting professor. Under his guidance, 7 students obtained the PhD degree, and his current research interest is non-linear dynamics and calculus of fractals. Welcome, sir. Without taking too much time, I will request Professor Gangal to deliver his valuable speech. Gangal, sir.
Thank you very much. Thanks for the kind introduction, and let me at the outset thank Professor Prashant Dade and Jaipurkar and other organizers for getting me into this meeting. Unfortunately, I could not personally come, but I hope whatever I can present will be seen as part of what I wanted to actually talk in person. Thank you very much. Topic of today's talk is fractional operators on fractals. And Professor Dade has instructed me to keep the focus on students and not experts. So as a result, what I'm going to do is avoid almost all the proofs, but focus on the ideas and try to explain as much as I can. Okay. These were my previous students. My program started with the first student, Porvankar, when we realized the need for developing a calculus on fractals. And the other 2 students, Abhay Parvati and Sima Satin, were involved in the development of calculus on fractals. What I'm going to do is to use constructions in calculus on fractals in order to define operators such as Riemann-Liouville operator, with which you must have been familiar for a long time, and yesterday a lot of people might have talked about it, to construct them on fractals. Okay. So fractional calculus is one of the most important branches of applicable mathematics at the current moment. While fractional calculus on the real line is studied very well, you must have heard it yesterday. It remains an interesting question whether it can be extended to fractal sets. And using the framework of calculus on fractals, which was developed some time back, the answer is yes. Of course, there could be more direct approaches. However, the approach that I'm going to present here is going to be a rather simple approach. So let us see. This is roughly the plan of the talk. We will first talk about calculus on two classes of fractals, and that will take some substantial time. After that, briefly discuss the notion of conjugacy of this calculus with ordinary calculus, and then use constructions in the conjugacy to talk about Riemann-Liouville operators. And of course, you could extend it to other operators on that. So what is firstly the motivation for calculus, for developing calculus on fractals? So there are a few questions that one can ask. For instance, what is the equation of motion of a particle moving in a fractal medium? Or what kind of a differential equation would model relaxation in glassy materials? What would be a differential equation satisfied by hindered diffusion? Of course, ordinary diffusion equation does not give such solution. What does a diffusion or more generally Fokker-Planck equation on fractal paths looks like? How does a Langevin equation on such paths look like? Another altogether different application could be that time is traditionally taken as a real value. The local structure of spacetime is then based on the model R1 cross R3. One could then ask the question that could this model be a fractal F cross R3? In other words, could the spacetime be such that the time component is now a fractal? Fortunately, all these questions that I listed, we could address them. And now, today we will talk about fractional operators. So before going ahead, let me give a perspective on different frameworks. All the undergraduate students are familiar with calculus in vector spaces, and which has many applications in physics such as mechanics, hydrodynamics, electrodynamics, and so on. The next stage is calculus on manifolds, and it is used as a tool in many places. For instance, in Hamiltonian dynamics, nonlinear dynamics, gauge theories, general relativity, Lie groups, and so on. Fractional calculus, about which you have been hearing since yesterday, has several applications in diverse fields. They are used typically for systems with memory, because there can be non-local operators which you can use to model systems with memory. So all these are the existing frameworks. Now what I'm going to talk about is calculus on fractals, and what could be the potential places where these could be used. So in complex systems, anomalous diffusion, Levy processes, fractal space-time structures and processes, time series, turbulence, disordered systems, path integrals, non-equilibrium systems, systems involving many scales, and so on. So these are the potential places where this framework will be of use. Now, what is the main problem in developing calculus on fractals? As we will see pretty soon, fractals are often too irregular to have any smooth differentiable structure defined on them. You are familiar with differentiable manifolds and calculus on manifolds, where the structures are smooth, whereas fractals are too irregular and they render methods of and techniques of ordinary calculus either powerless or inapplicable. Okay, which we will see with the help of a simple example. For instance, this is the example which we will use today. This is called the Lebesgue-Cantor staircase function. How is this constructed? So take a unit box between 0 and 1 on the horizontal axis and 0 and 1 on the vertical axis. On the middle third, at height half, draw a horizontal bar. Then there is a piece on the left of size 1/3 and a piece on the right of size 1/3. Again, go to the middle third of that and draw a horizontal bar at height 1/4 and at height 3/4. And keep doing this construction. Eventually, what you will get is a picture like this. Now, the interesting thing you will notice is that if this is the graph of a function, most of the places the graph is flat. Okay, in fact, that was the way we constructed it. If the graph is flat, it will mean that the derivative of the function is 0. And if you add all these intervals on which the graph is flat, it turns out that the length is equal to 1, the length with which we started. So here is a continuous function whose derivative almost everywhere is 0 because the graph is flat, yet it rises from 0 to 1. So this cannot obviously be solution of an ordinary differential equation because the derivative is 0. So these are the kind of problems that we have to deal with. Okay, this cannot be a solution. Now there have been many approaches to solve such problems: fractional differential equations, analysis on fractals, harmonic analysis using major theory. And these are the people who are involved in all this. But I will not go through all that. What we will do is, while these are all important developments, what we desire is something very simple, very direct, and as far as possible algorithmic. The calculus that I'm going to talk about now is constructed with this purpose. And at most places, it will remind you of ordinary calculus and ordinary undergraduate calculus that most of the students may have learned. And the construction is little bit extended, but not too much. So let us begin with a digression. Why this digression? Because actually Dr. Gade had told me that some students may not be familiar with fractals. So give a very brief introduction to that before going ahead. So what I will do is, rather than a most general introduction, I will take two prototype examples and try to develop concepts with these two prototype examples. Okay, one is an example of a fractal subset of the real line, namely Cantor's 1/3 set. These are only prototype examples, doesn't mean that the calculus that we develop is restricted only to this. It can be used in more general fashion. How do you construct this Cantor set? Start with a unit interval, subdivide it into 3 equal parts, throw away, delete the middle third, then you will be left with these two pieces. repeat the construction on each piece. So now these were pieces of length 1/3. After repeating it once more, you will get pieces of length 1/9 and so on. And keep repeating this ad infinitum. The resulting set is Cantor's 1/3 set. It has many interesting features. I will just list a few, but won't spend too much time on that. This is someone asking something? Uh, these sets are self-similar. That means if you take a piece and magnify it sufficiently, you will get the original set. It has fine structure. That means no matter how small scale you go to, you will again see structure. This set is uncountably infinite. It is closed, compact, disconnected, and it has length 0. So if you take the usual Lebesgue measure, one-dimensional Lebesgue measure, and try to make a measurement of length of this, that will turn out to be 0. This is very easy to see. How? In the first stage of construction, we deleted a piece of length 1/3. Then in the next stage, 2 pieces of length 1/9. Then 4 pieces of length 1/27, and so on. So sum this series 1/3 plus 2/9 plus 4/27 and so on and so forth. A simple geometric series, and you will see that the sum is 1. In other words, whatever is deleted has length 1. Therefore, what is left has no length. Okay. This is one example, and when I talk about fractal subsets of real line, I'm going to talk about sets like this, but not necessarily this set. Sets which are subsets of the real line, and we will later talk about the dimensions, and these will be having dimensions not equal to 1, but it turns out that this set will have a dimension smaller than 1. Another set which I will present now will have dimension bigger than 1, and so on. This second example is of what is called a Folkoff curve. This construction is again very simple. You start with a unit segment, take the middle third and draw a tent on that equilateral triangle without a base. And keep repeating this construction. This is the first stage, this is the second stage, and so on. Keep repeating ad infinitum. So you will get a set like this, a curve like this. Now the interesting thing you will note about this curve is that for the final curve, you cannot draw tangent anywhere. At finite stages, of course, you can see that this is flat, so it maps onto its tangent and this and so on. But when you construct and go up to ad infinitum, you cannot draw any tangent anywhere. So this curve represents a function without derivatives anywhere, for which derivatives cannot be defined. Now the third example is from physics. This is an example which I have, this picture is there in a book by Feynman and Hibbs on path integrals. You take a typical path, this small circle here uh, contains a piece of it, magnify it, it will look again wiggly like that. Take again a small piece of it, again magnify it, again it will look like that, and so on. So whether you deal with Feynman paths or Brownian paths, they all have this kind of what is called statistical self-similarity. Earlier, while dealing with Cantor set, I talked about self-similarity, but that was strict geometric self-similarity or This Fraunhofer also has a strict geometric self-similarity. If you take a small piece here and magnify it, it will look like the original curve. Here, on an average, the curve will look like itself. So these are examples of fractal paths. Now, how do I understand a little bit more about them? So what I will do is the following. Here, I consider a set which I have shown with a dark boundary, not necessarily a bounded set like that. Okay, there may not be a boundary, but for guiding I have drawn it like. Then I cover it with sets which I have called U1, U2, and so on and so forth. They are shown with blue circles, blue shapes. Okay, the construction that one can do is the following. Take the diameter of these sets Ui, raise it to certain power, which is called S, where this sets Ui is what is called a delta cover. That means the diameter of the largest of this, the largest diameter of this set is delta. And this construction is called the coarse-grained outer measure, coarse-grained Hausdorff outer measure. When you take, it can be shown that its limit will exist. When you take the limit, you get what is called the Hausdorff. Now, the interesting thing about this construction is the following, that if you consider a power t, which is bigger than s, and consider the sum of diameters of ui raised to t, and you sum over all the members of the cover, this is simply rewritten as ui raised to t minus s into ui raised to s. And since the diameters are less than delta, because this is a delta cover, I can replace this by delta raised to t minus s into a similar sum with exponent s rather than exponent t. Now take the infimum, you will get quantities like this, and ht delta will be less than t raised to, delta raised to t minus s into hs delta. So as delta tends to 0, if the right hand side, if this hs tends to a finite limit, recall what is hs? Hs is the limit of this. If this tends to a finite limit, then obviously the left hand side ought to be 0 for all s less than t. Now that is very interesting. That tells us that if you plotted hs, okay, versus s, then the graph is at infinity and it straightway jumps to 0 at one point and stays at 0 for larger values of s. This sharp point where the transition takes place is called the dimension of this set. Okay, and this need not be an integer. Okay, how do you understand this graph intuitively? You can very easily understand this intuitively. If you consider a two-dimensional region and try to take one-dimensional measure of that, that means draw number of parallel lines and keep adding their length, that will turn out to be infinite. On the other hand, if you consider a two-dimensional region and take the three-dimensional measure of that, volume of a two-dimensional region is going to be 0. So this is what we have learned in undergraduate geometry, that if you have only an appropriate measure, then you will get a non-trivial answer. If you consider a lower dimensional measure, the answer will be infinite. If you consider a higher dimensional measure, answer will be 0. Exactly that is being extended, except now I allow the dimension to be not just integer 1 to 3, but all possible, it takes all possible values. Okay, now our next job is to develop calculus on these kind of structures. Calculus on structures which are fractal subsets of the real line or fractal paths. Okay. This staircase function is going to play an important role in this formulation. I will show you how. So this digression was meant mostly for students who are not entirely familiar with Cantor sets and Polycockers and fractal subsets of real and fractal paths. So with this, let us now start. Okay. Now what I'm going to do will remind you about how you construct a Riemann integral on the real line. Okay. This is what you do in undergraduate calculus, except now that we are going to extend. We will first begin by constructing take a line. Okay. First, I'm going to develop calculus on fractal subsets of the real line, like Cantor-like sets. And these are, of course, embedded in a one-dimensional line. So, suppose if the set is is embedded between A and B, that means in the interval AB on the real line, then what I do is I subdivide the interval AB into a large number of small pieces, n number of pieces. This is exactly what you do for a Riemann integral. Okay. Have such a subdivision and then estimate the quantity which I have called sigma alpha. What is sigma alpha? Sigma alpha is the distance from xi to xi plus 1 is distance raised to some power alpha. This 1 upon gamma alpha plus 1 is for normalization purpose. We started actually with fractional derivatives. And you would have seen yesterday that this was always the normalization. So that I have kept the memory of that here. This is multiplied by a theta labeled by the fractal set and the interval between xi and xi plus 1. This theta takes value 1 if this interval uh, intersects the fractal in a non-trivial fashion. If the intersection is empty, then this is 0. So either the contribution here to the sum is 0 or xi minus xi plus 1 minus xi raised to alpha with this normalization. That is the contribution to the sum. This is exactly like what you do when you do the Riemann construction. Now these are the usual epsilon delta definitions that you use in the Riemann integral, except now we are dealing not with a length, but we are dealing with sigma alpha. This sigma alpha is the coarse grained length, okay, but with this corresponding new construction. In ordinary Riemann integral, this would be simply the length of the interval. Okay, this is my notation that when I say my draw two bars around P, it means maximum of the distance between xi plus 1 and xi. So in the partition, there are various pieces of various sizes. And this is the largest of them. Now what we do is we take this sum because here I have already sum. And now I vary the partitions. I consider all partitions whose diameter is less than delta and take the infimum of these partitions. This is what is called gamma alpha. Okay. There are some nice properties of this gamma alpha delta, which I will skip. Using this, it can be shown that this limit exists and we define gamma alpha to be the limit of this gamma alpha delta as delta tends to 0. This gamma alpha has nice properties. It is interval-wise additive. For instance, if you go from A to B and then from B to C and add a gamma alphas corresponding to that, you will get gamma alpha from A to C. So while this is not a measure, it has that nicety. It is continuous with respect to A and B, and in fact it is continuous in the whole interval between A and B. It has this translation and scaling properties. Scaling property is important for us because fractals have that character. And to fix our ideas about how does this gamma, how does it mean? What does it mean? This gamma turns out to be proportional to the Hausdorff measure if the set is compact. Otherwise, there is a difference between the two. You can again define, sometime back we defined a dimension using this HS. Similarly, you can define a dimension using this gamma alpha, which we call gamma dimension. And in this calculus, this gamma dimension, whenever we say that the dimension of a set is such and such, we are talking about the gamma dimension. These are the properties of this dimension. Now we come to the staircase function. Okay, and this staircase function, which we will define now, is a generalization of the Leibniz-Cantor staircase function that I showed you at the beginning. It is simply how this is defined. SF alpha is the staircase function. It is equal to gamma alpha from A0 to Bx if x is bigger than 0 and if it is A0 and if it is less than A0 then it is negative. Indeed, this staircase function, when you deal with Cantor set, exactly becomes the Lebesgue-Cantor staircase function. This is a notion that is a important technicality, but I will just say what it is and then go ahead. There are many sets which give rise to the same staircase function. Okay. So what we can consider is the set of change of the staircase function. What is a set of change? The point of change is that around which if you draw an interval, then no matter how small is the interval, the function necessarily changes. Okay, and that is the set of change. And then this alpha prefix set is the minimal such set. It is the minimal closed set corresponding to a given staircase. If you have the Cantor set which I showed you earlier, it is in fact can be shown to be alpha perfect. And calculus is all done with the help of that. How do I define an integral and a derivative? It's exactly as a Riemann integral that you undergraduate calculus. First, consider a function, and then on each interval, you find out how it is the largest value. Take the supremum of all such values. Now, the difference is that here, instead of just considering the interval I am considering the fractal set, its intersection with I, and nothing more. Exactly similarly, the small m is an infimum, and now we define this quantity, upper sum and lower sum. This is the upper bound that we have seen here, and this is the lower bound. In ordinary Riemann integral, this red bracket would be simply xi plus 1 minus xi. And now what I am having here is the difference in the value of the staircase function. That is the difference. Otherwise, they are exactly like in the Riemann. Now, you can consider the supremum of this L alpha and infimum of U alpha, and these will be the lower and upper integrals. If they turn out to be equal, we will say that the function is integrable and the common value is the integral. This is how I define a fractal integral. Do not confuse this integration with fractional integral. This is quite different. This is integral on a fractal. Later we will talk about fractional integrals also. It has nice properties. It is interval-wise additive. If you take the characteristic function of the fractal set and integrate it, it is exactly the difference between the values of the staircase function and so on and so forth. If you differentiate, if you, uh, let us come to the derivative, then I can talk about the derivative. When you consider derivative of a function, you consider a fy minus fx upon y minus x and then take the limit as y tends to x. Here I take the limit along the points in the fractal set, but the denominator is not y minus x, it is the difference between the values of the staircase. And when the limit exists, we call that the derivative. Okay, there are certain very nice properties of this. If you take the derivative of the staircase function, obviously you get the characteristic function of the fractal set. Then there are fundamental theorems of calculus which immediately generalize. For instance, if you consider a function fy and consider the fractal integral between a and x, and if this was derivative, if this is g, then you get derivative of that g equal to f into the characteristic function of the fractal set, and so on. So these are the fundamental theorems of calculus. One can of course have analog of a Taylor series. In the usual Taylor series, you would have this expression, but without the staircase function, w minus x raised to n into the derivative, nth derivative. Here I have this staircase raised to n being multiplied, and so on. So these are the properties. Now, to bring analogies with ordinary calculus, this is the next table. This is the calculus doing the usual Riemann integral, and this is what calculus we have for a fractal set. In the ordinary case, you have the real line as the domain or intervals of the real line. Here we are dealing with alpha perfect set. In the ordinary case, you take a limit. Here we take a limit by staying within the fractal set. That's why to indicate that you are within the fractal set, I have always put f in front of everything. Continuity, f continuity. If you consider a formula like x raised to n being integrated, you get y raised to n plus 1 upon n plus 1. Similarly here, if you integrate staircase raised to n, you will get staircase raised to n plus 1 upon n plus 1, and so on. Then there is a analog of Leibniz rule. There are analogs of fundamental theorems of calculus. Integration by parts, Taylor expansion, which I showed just a minute ago, and so on. Now here is an interesting concept, and this is crucial to what I talk next. This is the notion of fractalizing and defractalizing. I consider a set, I consider an interval between 0 to 1 and Cantor middle third set. This is only an illustration. This is not the whole story. You can do what is written here for this illustration can be considered, can be generalized. Excuse me. I consider any point of this J and consider a binary representation of that. So start with a binary point followed by string of digits x1, x2, etc., which are either 0 or 1. On the other hand, points of the Cantor set are represented in a ternary representation or a base 3 representation. The points of Cantor set are represented exactly similarly, except you don't use, see, in a normal ternary representation, you would get 0, 1, and 2. But I have now only 0 and 2. So you start with a ternary point. Here I started with a binary point followed by string of digits 0 or 1. Here I start with a ternary point and with digits which are either 0 or 2. Okay. Now, how do I map this Cantor set onto the real interval and vice versa? All I have to do is to take any number. Suppose I take this real number belonging to the interval 0 to 1. Wherever I find 0, retain 0. Wherever I find 1, make it 2. And in place of binary point, make it ternary point. You will get points of the Cantor set. And on the on the other hand, if I take a point of the Cantor set, all I do is the opposite. Start with a point, start with points represented using base 3 representation. Replace the point, ternary point by binary point. If the digit was 0, keep it 0. If the digit was 2, make it 1. So you will get back all the points of the interval. In this way, we can entirely map Cantor set to the interval 0 to 1 and vice versa. Now, induced by this, when I go from the interval 0, 1 to Cantor set, I call it a fractalizing transformation. When I go from Cantor set back to the interval, I call it a defractalizing. Induced by this transformation, we can actually go back to the functions. Okay. Here are some technical details, what function spaces I use and so on and so forth. Let us not worry much about that. But what can be shown is that the derivatives can be mapped on the appropriately constructed derivatives on the real line, and intervals can be mapped exactly in a similar fashion. And this can be shown. In fact, this requires a detailed proof. Through this diagram, consider a function, consider its fractional integral, you will get f1. Instead of that, if you consider the function, defractalize it, then you get function g. Consider an ordinary integral of that and then fractalize. You will get the same result. This is the meaning of the conjugacy that I explained by fractalizing and defractalizing. This is a numerical example for that. Whatever mathematics I told you about, you can put immediate confidence on that in view of this numerical verification. Okay, here is a function to guide the eye. Vertical bars are shown. This function is actually uh, sine 2 pi x into the characteristic function of the Cantor set. And then this is the plot. This is how the tip of all these bars is where the graph of the function line. Then defractalize it, integrate it, you will get like this, and then fractalize, you will get it like. On the other hand, if you stayed on the fractal and carried the fractal integral, you will get numerically like this. So this picture and this picture should, this and this should be equal if all that conjugacy that I showed you just now is true. And the difference between them is plotted here, and within numerical accuracy, the difference is 0. So this numerical verification of what we have done. I showed you about the integrals. Exactly similarly, you can take a function on the fractal, take a fractal derivative. Instead of that, you defractalize it, take ordinary derivative, and then fractalize it. You will get the same result. Okay. Now this was about the calculus that we developed for fractal subsets of the real line. You can use it for solving differential equations and so on and so forth. I will skip all that. We will now come to the fractal curves. And I showed you at the beginning example of Feynman paths, Brownian paths, polymer chains, percolating clusters, and so on and so forth. And transport on this structure is what is of interest. You can exactly similarly define mass and staircase functions, except that now staircase function is not looking like what staircase function I showed you earlier. So more appropriately, you can call it the rise function. A couple of examples of parameterized fractal paths. For instance, if you consider Weierstrass's nowhere differentiable function and plot its graph, this graph is a fractal curve. Indeed, my journey into fractional calculus started with by studying this function. What we could show is that this nowhere differentiable function is actually fractionally differentiable up to an order determined by the dimension of its graph. In fact, by what is called a local holder exponent. This is what example I showed you some time back, the von Koch curve. So we are now talking about calculus on such structures. Okay. Exactly similar to the calculus that we showed. We now start with a curve, which this curve is called W. And you recall the construction for Cantor set. We had raised the distance between Ti plus 1 and Ti, raised it to power alpha. Now this W is taking us to the fractal set. Exactly similar construction is done, where this norm, whatever are these vertical bars, it denotes the Euclidean distance. Carry through all the constructions that you have done earlier. In view of shortage of time, I will skip all that construction, but intuitively it is exactly like what we have been doing earlier. Okay, one can define the mass function. It turns out that this mass function is atomic. There are no singular contributions like delta functions on that. And it has nice scaling property. Okay, using this now, instead of staircase, I will prefer to call this as a rise function. Again, notation is same and construction is again the same for this rise function. This is for guiding the intuition. This is the numerically drawn graph in the plane below. This is a three-dimensional picture. In the plane below, this green curve that is seen is the von Koch curve, and the rise function corresponding to that is shown by bars above that, and this red is the rise function. Okay. You can do the calculus exactly in the similar fashion that we did for the Cantor-like states. I will skip this. Dimension can be similarly defined. And now we can come to the calculus. Okay. In particular, we can now talk about the integration. Exactly like what we did earlier, I am talking about the upper and lower bounds, supremum of f on the fractal paths and infimum. And then take this supremum multiplied by the difference between the values of the rise function. Similarly, the infimum and multiplied by the difference between the rise function. Take the limits of these upper and lower limits, and if they happen to be equal, then this upper integral and lower integral, if they happen to be equal, that defines the integral, which we denote by f theta with respect to d alpha theta. Again, I will emphasize this is not the fractional integral. This is the fractal integral. Okay. There are many nice results for this. For instance, if you take a segment of the fractal path between A and C and between C and D and add their integrals, it will be equivalent to integral on the segment between A and B, and so on. If you integrate one, you will get the difference between stated values of the rise function and so on. You can define exactly similarly the F alpha differentiation, except notice that the denominator is not theta prime minus theta, but the difference in the values of the rise function. Okay, fundamental theorems of calculus go through. And now we come to the conjugacy. These are the function classes. But I will skip that and I will assume that appropriate function spaces are used. And what does this theorem tell us? This is the important theorem for us, for what I'm going to talk in next 5 minutes before I stop. If a function is taken and it is integrable on the segment CAB of the fractal, if and only if the corresponding defractalized version is Riemann integrable on this interval, and the values of these two are exactly the same. So here on the left hand side is the fractal integral. On the right hand side is an ordinary Riemann integral. So if I have to evaluate this, I may actually evaluate this. Okay. What are A and B? They are simply corresponding to the values of the staircase function between A and B, where A and B are the points that I denote the fractal. Okay. This is the corresponding commutative diagram. Take F on the fractal, integrate it fractally. Instead of that, defractalize it, integrate, and go back. Similarly, for the derivatives, you can have a commutative diagram. This is the derivative commutative diagram for derivative. A Taylor series would work similarly. Now I come to the last point in next 3 minutes, and then I will stop. The formal construction of fractional operators on fractals. So far, I have not talked about fractional operators, such as Riemann-Leibniz operator. Just recall, you have been hearing about these fractional operators since yesterday. For instance, if you consider a Riemann-Leibniz fractional derivative, a fractional integral looks like this, where q is less than 0 and fractional derivatives they look like. Okay. There are nice properties. What I'm interested is in this last property. This property just says that the coefficient comes out. This says that you take sum of two functions, derivative becomes sum of the derivatives and so on. Look at the last property. This is the scaling property. So scaling property is built in the fractional derivative. And this is why fractional derivatives are also useful for dealing with the scaling process. Now I consider such kind of definition. Look at the right side. Think of them as if these are some ordinary integrals. And the right hand sides are ordinary integrals. So their meaning is that they are Riemann-Leibniz integrals. I use the part of this commutative diagram and recall that the integral on the fractal was computed by looking at the corresponding integral on the real line. Now what I do is the other way around. Take this because this commutative diagram takes me in both directions. So I start by considering the right hand sides in the Riemann-Leibniz definition like this. They are the fractional integrals and declare them now to be the fractional integrals of fractal. So this is how I construct Riemann-Leibniz integrals on fractal. What can be the potential use? So I will just remark in a minute about this and stop. If you consider the embedding Euclidean space in which a fractal is embedded and there is a process taking place on this fractal governed by a fractional differential equation. Okay. Then there are going to be two scaling exponents. One scaling exponent comes from the dimension of the fractal, and the other scaling exponent comes from the derivative, this Riemann-Liouville-like derivative. Okay, this is the. So now, if I forget about the details and observe the process taking place in a Euclidean space, I will see a process characterized by two exponents. And this is at the heart of potential use of such kind of construct. Okay, as I told at the beginning, I will talk about potential uses after the construction. So this is the use that if you want to deal with two scaling exponents, whether both correspond to the local behavior or a local and a non-local behavior, this is what you could use. Thank you very much for patient attention. These were the papers in which we have developed this formalism. Uh, this calculus on factor subsets of real line where conjugacy is there. This is where the formulation is developed. Okay. And of course, as I told you that initially I listed a number of problems like writing Fokker-Planck equation and so on and so forth. They are all in this. Let me thank you and stop here. If there are any quick queries, I may be glad to answer. There are only just some 2-3 minutes, so
Thank you, Professor Nangal sir, for delivering very much informative talk on the fractional operators on factors. His focus is on calculus of two-class factors and Riemann-Liouville factors. Now, any question from the audience?
Okay, Professor Kangal has been a legendary teacher both in Department of Physics in Pune University as well as ISER. I mean, generations of students still remember him, and I was very happy to have him here. If it would have been personal, it would have been great. I just didn't understand this alpha perfect state. We just maybe I should. Can you elaborate on alpha perfect state?
alpha perfect state. Yes. Okay. Let us go back. No, back. Further back. Okay. If you consider a given Cantor-like set and add a lower dimensional dust to it or remove a lower dimensional dust from the Cantor set. Say Cantor set is having dimension log 2 by log 3. But if I consider a lower dimensional dust and remove it from the Cantor set or add a few points to the Cantor set, which is of course lower dimensional, and find out what is the staircase corresponding to that. the staircase will be exactly the same. Okay, it is like the following. If you consider the real line and if you remove a few points, a lower dimensional set from the interval of the real line, calculus doesn't change. Integrals do not change the value. Okay, because you are having a lower dimensional set. In other words, it is like a set of measure 0. Now, instead of calling it a set of measure 0, I call it a lower dimensional set being removed or added. If you tamper the sets in this fashion, you still get the same staircase. So many sets will give rise to the same staircase function. This is exactly what happens in ordinary calculus also. So what is done now is consider all those sets with the same staircase function. And the minimal closed set corresponding to a given staircase function is what is the alpha perfect. So alpha perfect set is therefore suitable for calculating, formulating calculus. Okay, it can be formulated in the language of set of change. If you consider a point in the interval and enclose it in an interval, arbitrarily small size interval, if the function does not change on that, then it is not a point corresponding to the change. But there are points in which such a change does take place. For instance, let us go back to the staircase function. Let us ask the question, yeah, here was the staircase. Here the graph is flat almost everywhere. You can ask, where is the change taking place? It is taking place at such points of change. If I consider point in between here, okay, that does not correspond to a point of change. But points like this at the end point of the interval, they correspond to the point, set of points of change. And using such points, we can define the set of change. And the alpha perfect set is the containing all such points of change for the given staircase function. So this is what is a set. It turns out to be a perfect set. That is why it is called perfect. But it is, of course, characterizing the alpha dimensional structure. Therefore, instead of just calling it a perfect set, it is called alpha perfect set. Okay. But if you want more details, I will suggest that all its detailed properties are discussed in our paper calculus on fractal subsets of the real line. Okay.
Any more? Yeah.
Sir, is it possible to give the Laplacian operators on fractals?
Beg pardon, I did not get you. Is it possible what?
To give Laplacian operator on fractals.
Ah, yes, indeed. See, our construction starts with lowest order derivatives, but the construction that Richards and others, they don't start with lowest order derivatives. They start with a Laplacian. How can one directly define a Laplacian? Just try to recall the meaning of a Laplacian. What does a Laplacian measure? If you consider the function, if you consider Laplacian of a function at a point, and you consider a small box around it, then the Laplacian of the function measures the deviation of the value of the function at the given point from the average in that small box. Okay. So instead of, so if you take this is the standard meaning of the Laplacian. This is the standard interpretation of the Laplacian that we teach when we are teaching vector calculus, right? That Laplacian of a function gives a measure of the deviation of value of a function at a point from the average in a sufficiently small box. In fact, Laplacian is not a dimension-free quantity. It has dimension. So therefore, how small the box you should take? You should take sufficiently small box, then this is the meaning. So starting with this meaning, a Laplacian can be constructed directly. Okay, that is how Spichards and company and some others have started with Laplacians, not just on these simplest classes of fractals that I discussed today, but on more complicated classes such as Sierpinski gaskets and so on and so forth. So indeed it can be done.
So let us thanks to the renowned Professor Anil Gangal sir for such a wonderful speech. Thank you. Thank you.
Thank you very much and goodbye.
Yes, sir. Vote of thanks will be delivered after the two lectures. So you can. It's honored to hear from you. Thank you, sir. You can end the sessions.
Okay, thank you. And bye from here. Thanks to all.
Thank you, sir.